Hi everyone, my name is Kelly and I'm an AI Solutions Engineer at Intel, and today I'm very excited to share our Intel-optimized cloud modules for Microsoft Azure with you and walk through how you can deploy optimized distributed training workloads for large language models like nanoGPT. So first, let me share a little bit more about what the Intel-optimized cloud modules are. The Intel-optimized cloud modules are a suite of open source cloud-native reference architectures that bring together the different components of our software and hardware optimizations to facilitate building and deploying efficient and scalable AI solutions on the Azure cloud. The modules, or reference architectures, implement proven best practices for production AI development using popular open source AI frameworks. Each end-to-end AI reference architecture includes a full set of instructions with all source code, a white paper, and a cheat sheet published on our GitHub. We have currently released 4 AI-focused modules for Azure. The one that I'll be sharing today goes over the nanoGPT distributed training solution, but we also have others for Stable Diffusion, XGBoost on Kubernetes, as well as an XGBoost Kubeflow pipeline. You can deploy all of these modules from our GitHub that I've linked on this slide, or you can scan the QR code in the bottom right side of your screen. We have also published a dedicated site where you can find additional Intel-optimized cloud modules for Azure, on-demand videos, and register for our office hours on the Intel Developer Zone cloud landing page. Along with the AI modules I mentioned on the previous slide, we have an additional 9 modules to help you quickly deploy Intel-optimized Azure services, like a Databricks workspace or a Windows web app. And you can find all of these solutions on the Intel Developer Zone linked on this slide, or you can scan the QR code in the bottom right side of your screen. Okay, so now I want to share a little bit more about the solution that we'll be building today, fine-tuning nanoGPT in a multi-CPU environment. This solution demonstrates how to scale a standard single-node PyTorch training scenario into a high-performance distributed training workload across multiple CPUs. To fully capitalize on Intel hardware and further optimize the fine-tuning process, this module integrates the Intel extension for PyTorch and Intel oneAPI Collective Communications Library, oneCCL. This solution builds upon the nanoGPT implementation built by 𝗦𝗲𝗀𝗶𝗸𝗄 and has been refactored to achieve better modularity and suitability for distributed fine-tuning on 3rd or 4th generation Intel Xeon CPUs. The module serves as a guide to setting up an Azure cluster for distributed training workloads while showcasing a complete project for fine-tuning LLMs. The objective of this module is to understand how to set up a distributed training environment so that you can fine-tune the model to your specific workload. To form the cluster, the cloud solution implements Azure Trusted Virtual Machines, leveraging instances from the DV5 series. To enable seamless communication between the instances, each of the machines are connected to the same virtual network, and a permissive network security group is established that allows all traffic from other nodes within the cluster. The Open Web Text dataset is taken from Hugging Face Hub, and once the model has been trained, the weights are saved to the virtual machines. The result of this module will be a base LLM that can generate words or tokens that will be suitable for your use case when you modify it to your specific objective and dataset. And so now let's get into the demo. Okay, so before we begin, you'll just want to make sure that you have the Azure CLI installed for your operating system. And I'm running in a Windows subsystem for Linux terminal. And to check the version that you have installed, you can do az-version. And I'm running 2.4.6.0. And you can find all of the commands that I'll be running on our GitHub under the nanoGPT distributed training directory. So if you scroll down, you'll see the prerequisites that are needed, which is just a Microsoft Azure account and the Azure CLI installed on your machine. And then we can start setting up the Azure resources. So once you've logged into your account, we can create the Azure resource group. In the interest of time, I will copy this command to my terminal, and this will hold all the related resources for our solution. Okay, so now we'll create an Azure virtual network, and this will allow the virtual machines to securely communicate with each other. Okay, and next we'll create an Azure network security group. And this network security group will filter the traffic between the virtual machines in the network and allow us to SSH into the virtual machines in the cluster. Okay, and next we'll create our Azure SSH key pair so that we can securely connect to our VMs. Okay, and then I'm going to just change the privacy permissions of the SSH key. Okay, and now we'll upload our public key onto our Azure account. Okay, so now we're ready to create our first virtual machine in the cluster to fine-tune the model on a single node. So we'll be using the SSH key, virtual net, subnet, and network security group that we created in the previous steps. And for the VM size, we'll be using the standard D32V5, which is an instance from the DV5 series. And these are third generation Intel Xeon scalable processors that feature the Intel Advanced Vector Extensions AVX512, Intel Turbo Boost technology, and Intel Deep Learning Boost. And for our workload, we'll provision 32 virtual CPUs with 128 gigs of RAM, and we'll also provision 256 gigs of storage. Okay, and now we'll SSH into the machine. Okay, and now we can install our dependencies and activate our conda environment. Okay, and now we're ready to install the required packages for the module. And to do that, I'm going to clone our GitHub repo. And now change directory. Now we'll pip install the requirements. Okay, and now we're going to download and install the oneCCL library. Okay, now we're ready to prepare the full open web text dataset. Okay, so now that our dataset is prepared, we're ready to fine-tune nanoGPT on a single node. And to streamline this process, we will use the Hugging Face Accelerate library. So to generate the config file for Accelerate, we will use the accelerate config command. And we will call our single config. Okay, and then it'll ask us a few questions here. So the first one, we'll select this machine, no distributed training, and then we'll select yes. And yes, we do want to use Intel extension for PyTorch. And then since we're on a 3rd gen Xeon, we'll select FP16. But if you are on a 4th gen Xeon, you can select BF16. Okay, and now we're ready to fine-tune the model. And to do this, we'll use the accelerate launch command. Using the configuration file we generated to initiate the fine-tuning process, Accelerate will automatically select the appropriate number of cores, device, and mixed precision settings based on the options that we selected earlier, helping us to streamline the process and optimize performance. Now that the fine-tuning process has begun, it will train the model for a specified number of iterations and perform evaluations at regular intervals. In this demo, it is set to every 5th interval. If the evaluation score surpasses the previous iteration's performance, the model will be saved in the current working directory, and it will also save the snapshot of the training progress under the name snapshot.pt. Using the open web text dataset, the model will be fine-tuned for a total of 10 iterations using a batch size of 32. These settings can be easily customized by modifying the values in the configuration file. Once the model completes the fine-tuning process on the single node, then we'll be ready to scale up the training in a distributed setting across multiple nodes. Okay, now we're ready to set up our environment for distributed fine-tuning. So I will first get the private IP address of our machine by using hostname-i, and then we'll set up the multi-config acceleration file. So I'll select this machine, and then I'll select multi-CPU. We'll use 3 nodes, and this will be rank 0, and the IP address of this machine is 10.0. And we'll use port 29500. And then we'll select no. We'll use static and yes. And the question about the number of CPUs to be used is actually about the number of CPU sockets. And for this instance, we have one CPU socket, so we'll select one here, and then we'll select FP16 again. Okay, so now we're ready to create our 2 additional virtual machines in the cluster for distributed fine-tuning. And to do this, we will create a disk snapshot from this virtual machine. So I'm just going to go back to my terminal. So the first thing we'll create is our Azure snapshot. Okay, and now we'll create an Azure Compute Gallery to store the virtual machine image definition and image version. Okay, and now we're going to create the image definition and store it in the Azure Compute Gallery that we just created. Okay, so now that we have our disk snapshot and image definition created, we can create our image version. Okay, now that we have our virtual machine image created, we can go ahead and spin up our 2 additional VMs. And we'll use the same VNet, subnet, and network security group that we created earlier. And we'll keep the VM size the same. Okay, so now that our 2 virtual machines have been set up, I'm first going to configure passwordless SSH between the machines. So first I'll log into the second VM that we created and get the private IP address. So that is 10.0.0.5, and then I'll get the third one. So that's 10.0.0.6. Okay, so from the master node, I'm going to create a file called config in our SSH directory. Using the private IP addresses. So for the host, that is 04. For node 1, that is 05. And node 2 is 06. Okay, now we can check that the passwordless SSH was configured correctly by doing SSH node 1. Awesome. And then we can do SSH node 2. Okay, awesome. Okay, and on the master node, we'll also want to create a file called hosts. That will contain the name of the nodes that will be used during the fine-tuning process. So we'll use localhost for the master node and node 1 and 2 for the 2 additional nodes that we just created. Okay, and before we begin the fine-tuning process, we first just want to update the multi-config file in the other 2 nodes and change the rank. So on node 1, we'll change the rank to 1. And in node 2, we'll change the rank to 2. Okay, and so now we just want to activate the con environment in each VM. And then we'll set the oneCCL environment variables that will enable the distributed training using Intel MPI. Okay, so now we're ready to launch the distributed fine-tuning process using the Intel MPI library. So we'll use this MPI run command. And this will look for the names of the nodes in the host file that we created earlier and set the number of nodes to 3 with 1 process per node or 1 training job per node. And it will also set an environment variable that will apply the libtcmalloc performance library to all of the processes. And we've also set the number of CPU threads that PyTorch will use to 16, which is the number of physical cores in our machines. Okay, while that's running, I'm going to use htop in each machine so we can see the CPU usage during the fine-tuning process. Using the NPI run command enables parallel processing across multiple nodes, which facilitates efficient utilization of computing resources and helps to accelerate the model training and data processing. MPI run can be used not only for distributed training, but it can also be used to run programs that execute parallel applications across multiple nodes or machines, leveraging the capabilities of the Message Passing Interface Library, MPI. The Intel MPI library enables you to create, maintain, and test advanced applications that have performance advantages on high-performance computing clusters based on Intel processors. Similar to the single-node fine-tuning, the model will be trained for 10 iterations using a batch size of 32. Once an iteration is completed in each of the 3 nodes, the training loss will be reported on the master node. The training loss from iterations completed on the master node are shown as rank 0, and the training loss from nodes 1 and 2 are shown as rank 1 and 2. And now we'll let the fine-tuning process complete 10 iterations across the 3 nodes, and then we'll use the fine-tuned nanoGPT model to run inference and ask questions. Okay, now that we've fine-tuned the model, we can perform inference using the sample.py script included with this repo. So the command to run inference is python sample.py, and we'll send it the checkpoint path and the prompt. And there's the generated response. And that concludes this demo of fine-tuning a large language model in a distributed architecture on the Azure cloud. Thank you very much for watching and attending Microsoft Build, and we look forward to staying connected with you on our social media handles linked on this slide.